Hi, grade 11s, and welcome to the second session for the winter school. Today we're going to be looking at the mole, which is the unit for measuring amount of substance. So I'm going to start off straight away by saying, if you're talking about the number of moles, you're doing it all wrong. There are different things we measure in science. There are the fundamental quantities such as length, mass, time, temperature, electric current, and amount of substance. The mole is the SI unit for the amount of substance, just like the meter is the SI unit for length, and so on. Now, how big is one mole? Okay, so I know that the concept can be very confusing because of the confusion between the number of particles and its the mass that it's weighed and so on. But this is a very interesting video that will help you understand some of the important things you need to know about the mole concept.
Okay, today we're going to talk about the mole. Now I know what you're thinking. I know what a mole is. It's a small, furry creature that digs holes in the ground and destroys gardens. And some of you might be thinking that it's a growth on your aunt's face with hair sticking out of it. Well, in this case, a mole is a concept that we use in chemistry to count molecules, atoms, and just about anything extremely small. Have you ever wondered how many atoms there are in the universe, or in your body, or even in a grain of sand? Scientists have wanted to answer that question, but how do you count something as small as an atom? Well, in 1811, someone had an idea that if you have equal volumes of gases at the same temperature and pressure, they would contain an equal number of particles. His name was Lorenzo Romano Amedeo Carlo Avogadro. Wonder how long it took him to sign autographs. Unfortunately for Avogadro, most scientists didn't accept the idea of the atom, and there was no way to prove he was right. There was no clear difference between atoms and molecules. Most scientists looked at Avogadro's work as purely hypothetical and didn't give it much thought. But it turned out he was right. By late 1860, Avogadro was proven correct, and his work helped lay the foundation for the atomic theory. Unfortunately, Avogadro died in 1856. Now the thing is that the amount of particles in even small samples is tremendous. For example, if you have a balloon of any gas at 0 degrees Celsius and at a pressure of 1 atmosphere, then you have precisely 602 sectillion gas particles. That is, you have 6 with 23 zeros after it particles of gas in a container. Or in scientific notation, 6.02 times 10 to the 23rd particles. This example is a little misleading because gases take up a lot of space due to the high kinetic energy of the gas particles, and it leaves you thinking atoms are bigger than they really are. Instead, think of water molecules. If you pour 18.01 grams of water into a glass, which is 18.01 milliliters, which is like 3.5 teaspoons of water, you'll have 602 sectillion molecules of water. Since Lorenzo Romano, never mind, Avogadro was the first one to come up with this idea, scientists named the number 6.02 times 10 to the 23rd after him. It is simply known as Avogadro's number. Now, back to the mole. Not that mole. This mole. Yep, this number has a second name, the mole. Chemists use the term mole to refer to the quantities that are at the magnitude of 602 sectillion. This is known as a molar quantity. Atoms and molecules are so small that chemists have bundled them into groups called moles. Moles are hard for students to understand because they have a hard time picturing the size of a mole, or a 602 sectillion. It's just too big to wrap our brains around. Remember our 18.01 milliliters of water? Well, that's a mole of water. But how much is that? Exactly what does 602 sectillion look like? Maybe this will help. Exchange the water particles for donuts. If you had a mole of donuts, they would cover the entire Earth to a depth of 8 kilometers, which is about 5 miles. You'd really need a lot of coffee for that. If you had a mole of basketballs, you could create a new planet the size of the Earth. If you received a mole of pennies on the day you were born and spent $1 million a second until the day you died at the age of 100, you would still have more than 99.99% of your money in the bank. Okay, now we sort of have an idea how large the mole is. So how do we use it? You might be surprised to know that chemists use it the same way you use pounds to buy grapes, deli meat, or eggs. When you go to the grocery store, you don't go to the deli counter and ask for 43 slices of salami. You buy your salami by the pound. When you buy your eggs, you buy a dozen eggs. When we hear the word dozen, we probably think of the number 12. We also know that a pear is 2, a baker's dozen is 13, a gross is 144, and a ream of paper is... anybody? A ream is 500. Well, a mole is really the same thing. For a chemist, a mole conjures up the number 6.02 times 10 to the 23rd, not a fuzzy little animal. The only difference is that the other quantities are more familiar to us. So there you have it, the story of the mole, Avogadro, basketballs, and how to buy salami at the grocery store.
If you've ever been with your parents shopping, you know that you can go to places like Checkers and Pick n Pay and you will buy the fruit there per kilogram. So you would buy like 2 kilograms of tomatoes for so much money, or 3 kilograms of apples. So there you buy per mass. So that is one of the ways we can think of when it comes to the mole. We are able to, by mass, determine the number of particles. If you buy on the street from the vendors, you will buy a plate. A plate will have 6 bananas, or a plate might have 12 oranges, and you pay per plate because you're buying there per number. So the mole is also a number. So we're going to look at how we can use this idea to help you understand what the mole concept is and get a better understanding of how it's used in chemistry. So we're going to start off with this very short activity that I devised to help you understand the mole as a counting unit. So there are 5-cent coins. I've got a dozen 5-cent coins. In other words, 12 5-cent coins. There I have a dozen 10-cent coins. So 12 10-cent coins. Now remember, the 10-cent coins are smaller than the 5-cent coins. And what I've done there is I've taken the mass of a dozen 5-cent coins, and that is 54 grams. So the mass of a dozen 5-cent coins is 54 grams. The mass of a dozen 10-cent coins is 24 grams. So that is the mass of a dozen 10-cent coins, 24 grams. So the first thing I would like you to do is to find out how many dozen coins, 5-cent coins, do I have in that envelope that has a mass of 216 grams. There I've got the 10-cent and 5-cent piece masses there for you to be able to work it out. So that's the first thing. For the 5-cent coins, now here's another one. It has a mass of 135 grams. How many dozen 5-cent coins are in that envelope? Now moving on to 10-cent coins. In that envelope, I've got 48 grams of 10-cent coins. How many dozen 10-cent coins are in that envelope? And then finally, in the last envelope, we have a mass of 12 grams of 10-cent coins. How many dozen coins is that? So I would like you to do that first, and this is the first part of the worksheet for the activity. So grade 11. So I hope you see from that activity that the mole, it's useful to look at it or to see it as a counting unit. Just like when we talk about a pair, how many shoes? Yes, that's 2. A dozen refers to how many donuts or eggs? 12. How many pencils are in a gross? Well, 144. How many pieces of paper are in a ream? 500. So in chemistry, the mole can be considered as our counting unit. But I want you to remember that it is one of the 7 base units that we measure all things in. So amount of substance is the quantity we measure, and its unit is the mole. Now, because I know that stoichiometry can be hard, one day myself there in my lab with a scale and a storeroom full of chemicals, asked my grade 11 students a question. Would a teaspoonful of different elements have the same mass? And I'm asking you that question now. Would a teaspoonful of these different elements have the same mass? Well, let's see. There I took 1 teaspoonful of carbon, it had a mass of 0.22 grams. A teaspoonful of magnesium had a mass of 0.04 grams. Of copper had a mass of 0.46 grams. The teaspoonful of calcium had a mass of 0.15 grams. Of zinc, 0.49 grams. Of iron, 0.56 grams. Of sulfur, 0.14 grams, and of lead, 1.08 grams. So I did this with my class just like I'm doing with you. So there are the results in a table format. Now, there are different ways that we can calculate the amount of substance in moles, and this is one of the ways. If you know the mass, you can calculate the amount of substance. You will need to use the molar mass of that substance to calculate amount. Remember, where do we find the molar mass? You go to the periodic table. The mass number, that number for the element, is the mass for 1 mole of substance. So, for example, carbon will have a molar mass. If you look on the periodic table, the mass number is 12, so it has a molar mass of 12 grams per mole. Now, grade 11, so you're going to be using that mathematical relationship. The amount of substance N, measured in moles, is equal to the mass of the substance divided by the molar mass. Remember, the molar mass will be found on the periodic table. So carbon, if you look on the periodic table, has a mass number of 12. Its molar mass is 12 grams per mole. I want you to work out the amount of substance in moles that I had in 1 teaspoonful of each of these substances, and there the mass is given to you. When you have finished finding the amount of substance of these different elements, we will do the same for compounds. So after this activity, it might be good to take a short break.